Good afternoon, ladies and gentlemen. Today we're going to be talking to you about the synthesis of zinc oxide nanomaterials via solution synthesis methods. I'm Jackie Feng.
I'm Lawrence Choi.
I'm Alexi Owen.
And I'm Soham Pawar. Let's begin.
So first we're going to give you a brief overview of what we're going to talk about today. The first thing we're going to look at is zinc oxide and the concepts behind the field of nanotechnology. Next, we're going to take a look at solution synthesis, the specific synthesis method that we used in our experiments. After that, we're going to analyze our results briefly, and finally, we're going to draw some conclusions from the data that we observed.
So we're going to be talking a lot today about nanotechnology and nanomaterials. But before we do that, it's important to get an idea of what exactly the word nano means. So meet nano, a 1 preceded by 8 zeros, 10 to the negative 9th power. And that's a really small number, so let me put it into perspective for you. A nanometer is to a meter as a marble is to the diameter of the entire Earth. How's that for scale?
So what exactly is zinc oxide? Well, it's a semiconductor compound that has a work-site crystal structure, which is the figure shown to the right. And this means that it is composed of ZnO4 6- tetrahedrons that are stacked in such a way to reproduce this hexagonal structure. When you shrink zinc oxide down to the nanoscale, its properties become very size and structure dependent, which means by changing the morphological conditions during synthesis, you can produce a wide variety of structures that have finely tuned properties. And one of these properties that is pervasive amongst almost all of these structures is quantum confinement. And what this means is that when the de Broglie wavelength associated with the electrons starts to become larger than the actual nanostructures, the electrons are confined in 1, 2, or 3 spatial dimensions. And this results in a number of unique properties that enable zinc oxide nanostructures to be used in a wide variety of applications.
So key to those applications are the electrical and optical properties of zinc oxide. First up is piezoelectricity. This is the buildup of charge that occurs when mechanical stress is applied to the nanostructures. Next is field effect transition. Now, zinc oxide nanostructures actually have the ability to amplify and switch current acting as transistors. Zinc oxide can also be used as a chemical detector, detecting anything from gases to elements to biological agents. It's also photoconductive, which means that when an ultraviolet radiation is applied to it, it actually increases in conductivity, a very useful electronic property. And finally, zinc oxide is photoluminescent, which means that under certain conditions, it can actually emit ultraviolet radiation or even visible light. Now, one of the main things that we studied in our research were the nanostructures, the actual morphologies of these structures. So there's a couple of common ones: belts, spirals, helices, cones, stars, tubes, and cages. But the one that we majorly focused on were nanorods. And these are super versatile structures. They're the hexagonal things that you see over here. And they have a lot of electro-optical properties that make them very, very useful. So we've talked a little bit about the research. We've talked a little bit about the background. What actually was our objective from this research? We had 2 primary goals. First was to investigate the effect of various variables of solution synthesis on the actual structures we form. And next was to take those structures and explore the applications in the real world. Here's how we did it.
So many conventional synthesis techniques for making zinc oxide nanostructures utilize vapor transport processes. But this occurs at very high temperatures, upwards of 1,000 degrees Celsius, because you need to generate zinc and oxygen vapor. What we studied in our research was solution synthesis, which deals with aqueous solutions and occurs at much lower temperatures that are usually below 100 degrees Celsius. So they're much more cost and energy efficient when compared to traditional processes. The specific reaction that we were dealing with was a reaction between zinc nitrate and urea, and it's outlined right here. We used urea to have a very finely controlled release of the hydroxide ion, which affects the basicity of the solution, so we didn't produce bulk zinc oxide. And in the second step of the reaction, zinc ions that were in solution reacted with carbonate ions to produce a basic zinc carbonate precipitate, which was deposited upon a copper wire. And when this was subject to thermal treatment, or if it was heated, we formed our desired zinc oxide nanostructures. Now, in the second part of our experiment, we doped these zinc oxide structures with tin, which means we incorporated tin ions into the crystal structure that you saw earlier. And this happens according to the reaction here, where the hydroxide ion, tin ions, and zinc ions react to form zinc tin oxide or zinc stanate.
So now moving on to our own experimental procedure. To prepare solutions, crystals of urea and zinc nitrate hexahydrate were mixed with distilled water in Pyrex beakers. 2 copper wires were placed in each beaker in order to serve as the substrate on which the nanostructures could grow. And aluminum foil was used to cover the beakers in order to prevent water loss during the heating process. And as you can see from this picture of our experimental apparatus, a hot plate was used to facilitate heat transfer to the solutions, while a thermocouple was used to monitor temperature. And because we could not stay in the laboratory for extended periods of time, we used a digital programmable timer in order to automatically turn on and turn off the hot plate and control the duration of our reactions. So the variables that we manipulated throughout the course of our experiment were the following. Concentration of urea, this was trials 2 through 5. Concentration of zinc nitrate hexahydrate, trials 6 through 9. Reaction temperature, trials 10 through 12. And reaction time, reaction duration, trials 13 through 17. And after the effects of altering these 4 variables were thoroughly tested with these 17 trials, those initial 17 trials, we ran 3 doping trials in order to see the effect of a dopant, tin, on the nanoscale morphological and electric properties of zinc oxide spinels. So we introduced different concentrations of stannous chloride into solutions of urea and zinc nitrate according to this table. And the method employed was consistent with the method of the first 17 trials, of course without the addition of tin. And after we had performed our synthesis reactions, we of course had to observe and analyze what exactly it was that we created. So we went to the microscope lab where we had 2 different analytical tools available to us. First was a FESM, or the Field Emission Scanning Electron Microscope. And this allowed us to both take pictures and make measurements at the nanoscale. The EDS, or the Energy Dispersive Spectrometer, allowed us to confirm the elemental composition of our synthesized nanostructures. Moving on to results. So for our initial trial, we reacted very low concentrations of both urea and zinc nitrate hexahydrate at a relatively low temperature of 60 degrees Celsius. We did not synthesize the hexagonal nanorods that are characteristic of zinc oxide nanostructures. Rather, they were partially formed with a regular structure, as you can see here. And although we did not synthesize hexagonal nanorods, our initial trials still effectively served as a baseline from which we could revise our reaction conditions and optimize our experimental matrix. And the white particles that you see on the edge of this semi-hexagonal nanostructure are simply clusters of zinc oxide particles that were not incorporated into the overall semi-hexagonal structure.
So following the initial trial to form hexagonal nanorods, we began our first set of trials that varied the concentration of urea. In this case, we decided to adjust our variables upwards, changing our temperature from 60 degrees to 90 degrees, and increasing our time as well in order to produce more fully formed nanorods. As you can see from this first image, we have a trial with a concentration of urea that was relatively low, so the hexagonal basal facet is not as nearly defined. The basal facet of the nanorod is the facet that's parallel to the copper substrate. And if you go to the next picture, you can see that a trial which occurred at much higher temperatures had much more structural definition, and you can also see a definite increase in diameter and length of the nanorods. The next image displays a much more zoomed out FESM picture, and you can see to the right of the image that you see large conglomerated structures. These splinter-like structures were observed in trials 2 and 3 of our experiments, and they occurred at relatively low concentrations of urea. They appear to be composed of porous, shredded fragments, as you can see in the image, and they occurred beneath the nanorods and above the substrate. As you can see, they had no apparent orientation relative to the substrate, and they had highly irregular structure. Next, we have an EDS spectrum of these structures, which we use to confirm the elemental composition. And you can see that we have distinct peaks for zinc and oxygen. You can also see in this image that you have a carbon peak and a copper peak. The carbon is from the carbon tape that we use in our FESM equipment, and the copper is from the copper substrate. Our next set of trials varied the concentration of zinc nitrate hexahydrate within the solution, which was the other reactant. And the primary trend that we observed during this set of trials was that the orientation of the nanorods relative to the substrate became more regularly perpendicular as the concentration of zinc nitrate increased. So as you can see in this image from a trial which had a low concentration, the nanorods are relatively irregular in terms of orientation. And if you look at one of the trials that occurred later on, you can see that they're much more perpendicular, and we believe that this is due to the concentration increasing. We also observed several structural variations among the nanorods at different concentrations. At the lower concentration, we found intersecting nanoplates, which were visible in the first picture. And at this higher concentration, you can see that there are compressed heterogeneous forms above the nanorods, and we postulate that these were formed from nanoparticles.
So in our next set of trials, we varied the temperature of the synthesis of our nanomaterials. And we found that there was a correlation between the temperature and the quality of the nanorods, with a higher temperature conferring a greater quality. We also found that 90 degrees Celsius was the optimal temperature of the ones that we tested for the synthesis of nanorods. So as you can see in this picture here, which occurred at a low temperature, the quality of the nanomaterials was very low, but as we increased the temperature, the quality became much higher, and we observed the structural integrity that we found in our other trials. And we also found that there was a correlation between the duration and the size of the nanorods, with a longer duration resulting in a larger diameter and length. Additionally, we found this dark area, as you can see on this picture, that we had not observed in any of our other trials, and it's postulated that this was the result of excess ions in the solutions used for synthesis were deposited upon the copper substrate. Additionally, we found that there were structural variations in this dark area in the nanorods, as you can see with these ridges, that was not present in any other areas of the wires or on any of our other trials. So in our final set of experiments, we introduced tin as a dopant for our zinc oxide nanomaterials. Instead of obtaining the hexagonal nanorods that we had observed in our other trials, we observed rectangular nanorods. Additionally, we obtained these spherical nanoparticles, as you can see in the picture, that were not incorporated into the regular structure of the nanorods. Additionally, after conducting EDS analysis, we observed the characteristic peaks of zinc, tin, and oxygen that indicated that we had successfully doped our zinc oxide with tin to form zinc stannate.
So there are still several areas for improvement in our experimental procedure. The equipment that we use, namely the electronic balance that we use to measure out the masses of reactants, hot plate that was used during the heating process, and the wash bottles with which we transferred distilled water to our solutions, all could have been much more precise. And ideally, if we had more time in the microscope laboratory, we would have had more room for investigation with both the FISM and EDS tools.
So now that you've taken a look at our research, taking a look at our data, what conclusions can we draw from this? Well, to start off, we can successfully report that we did in fact complete both of our primary objectives, investigating the effects of various variables on the structures generated and exploring the applications of those structures. This occurred over the course of 20 experimental trials and produced nanostructures ranging in size from 40 nanometers to 1 micrometer. Now, we had a number of experimental findings from our research. First off, we recognized that if you increase the concentrations of urea or the duration of the actual synthesis process, you'll see a corresponding increase in diameter and length. Similarly, if you increase the concentration of zinc nitrate, you'll see an increase in the perpendicularity of the actual structures. We also discovered that 90 degrees Celsius does appear to be the optimal temperature for solution synthesis because it's right under the boiling point of water. We also discovered a number of potential applications, which leads us to our next section. Looking to the future, what can we do with this research? Well, obviously, there's a number of synthesis methods that can be revised using this. We've demonstrated a number of optimal conditions for solution synthesis, and that can be applied to further enhance the process. There's also a number of interesting applications that came out during our research. Using the nanorod structure to test the electro-optical properties of the zinc oxide, we can actually test the ability of the structures that we generated to act as field emission transistors in electronics. We can also measure their optical waveguiding abilities to see how well they'd act as a UV emissions device or as a laser. And finally, by suspending these nanoparticles in some kind of a solution, we can use that as reactor coolant in a nuclear reactor and use it to moderate the critical heat reflux, or CHF, in the reactor, which will effectively reduce the risk of overheating. With that, ladies and gentlemen, this has been the synthesis of zinc oxide nanomaterials. Before we go, though, there are a couple of acknowledgments we'd like to make to the people who made this possible. First off, Professor Stephen Desai from Rutgers University for his leadership. Dr. Zizong Dong, also from Rutgers, for his guidance and his instruction. Mr. Babangala, our RTA, for being the most wonderful, engaging, enthusiastic person you ever could have asked for. Dr. Eileen Rosen and Mr. Jean-Patrick Antoine of the Governor's School for making all of this possible for us. And our 2013 GSAT sponsors, the State of New Jersey, Rutgers University, Morgan Stanley, New Jersey Resources, South Jersey Industries, PSENG, and of course, the GSAT alumni community. Ladies and gentlemen, we thank you for your time, and we're happy to answer your questions. In the back.
Of the applications you mentioned, which do you think is the best what do you think you can apply it the best?
Well, the good thing about our research is that it's very fundamental. So we've demonstrated that there's certain inherent characteristics, size, structure, that can be applied to a variety of different things. So you can have electronic applications, you can have optical applications, you can have nuclear applications. And really where we go from here is what we describe in our future work, where you have to test those characteristics directly. So test its ability in a transistor, test its ability in a reactor.
And specifically, based on past literature, nanorods work especially well as field effect transistors. So that's probably these nanostructures in particular have very good electrical properties.
So is it generally true that if the structure appears to be more symmetric and more sharply defined, that it's better at all of those applications, or are there some applications that it matters more than others?
That varies from application to application. Alexei mentioned field effect transistors. For transistors, you really want a very defined structure, so that, like the ones we got in a higher concentration. But for other things, like for example using it in reactor coolant, you just need a particle of some kind. So that really varies based on the application. But in general, yes, more defined is better.
And also those particles that we were showing initially in our first trial that are not very well formed, those are actually used in all of your sunscreen products nowadays, is very small nanoparticles rather than these complex nanostructures. And as a result of these small particles, that eliminates the white color that's usually associated with sunscreen.
It's also used in antimicrobial things for jackets. So there's a lot of applications, but it really depends on what you're using it for.
You mentioned that increasing concentration increases the particularity, right? Is there a cutoff at which point that stops to happen, or there's a maximum concentration at which point you still get a further increase, or could you explore that further?
Well, we're talking about perpendicularity, so obviously the cutoff is going to be a perfect perpendicular 90-degree angle. But we didn't actually have enough resources to go and measure it step by step all the way up. But yes, that from what the trends we observed, that would be the case.
So you didn't find an actual maximum concentration?
No, that would require some more testing. All right, thank you.